Let me just make this thing bigger. Yes, it is here. All right. So inference optimization, as I was saying, is about making the interaction between the model and the user that is using the model, maybe through an app, faster. So today we'll talk about the basics of it. The chapter is divided into bigger into like main sections. One is called Understanding Inference Optimization, which is talks a bit more about like general things about inference, perhaps not at the beginning, not super related about model inference, and more of the engineering problems. So we will discuss computational bottlenecks, online and batch inference APIs, then a bit more about inference performance metrics, uh, and a bit of how hardware, which here we refer to it as AI accelerators. And then more on the model side, we'll talk about model optimization, in the sense of the type of optimization that improves latency and inference, not specifically the type of optimization that improves accuracy or performance metrics. Um, and we'll also discuss about inference service optimization. So when building a model, in the model lifecycle, there's two main things. One is training, which is building the model. And the second one is inference. So it's using a model to compute an output for a given input. So basically, after we have a model that we know that it works, that it was trained, that we tested, we evaluated on some data. We want probably to put it out there, to put it in production, and then we care about inference, right? Because we want to provide a fast and accurate result to users, right? So that's where inference comes in, and inference optimization is about making these models cheaper and faster. And why do we want to make them cheaper? Because if the model is too expensive, then its return on investment won't be worth it. It's always good to remember that models address a or should address a business problem, right? Should provide some value to the end users and ideally to the company as well. So if the model then is too expensive to run for a company, every time a user uses it, then the return won't be enough, right? So it would be costing money to the organization, to the company, to the service in general. So yeah, that's one of the main motivations about like why we want to make it cheaper. And of course, faster, we also want to make it faster because that improves general user experience, right? Let's imagine you go to ChatGPT and you ask it to summarize a document, and if it takes a day to summarize it, then probably if a new competitor comes out and it takes 2 minutes, then you go and use the one that is faster, right? Yeah. And this type of optimization, inference optimization, can be done at several levels, different levels, at model level, at hardware level, and at service level. So model level, usually model researchers are the ones that work there trying to optimize the model or try to optimize the inference parts of the model. Then there's also hardware stuff that we could do. And here's where hardware architects comes in, maybe compiler designers. So they write a specific compiler that is better for this type of architecture and this type of hardware that's gonna run in. Then service level, we have data centers optimized to run this type of queries. We have system engineers, etc. So at the end, this is like this type of optimizations are very complex, right? And it requires uh, many different people with different like backgrounds and specialties. If we want so if we want to see it as an image, as I was saying, uh, the inference optimization is about making this interaction faster, right? So we usually have an inference service, a server that it's basically a component that runs the model inference and it hosts the available model and has access to the necessary hardware. So let's say that we have here three models. They run on top of a specialized hardware, and there's an application that connects to these models. A user makes a request or the application makes a request and the model returns a response. So basically the job of this inference service is to allocate resources to execute the appropriate models and return the responses to the users. So here we decide, okay, this request goes to model one, two, or three, or maybe goes to three of them and they vote, or maybe, I don't know, there's a different system there happening. But the idea is that this interaction happens in a fast and cheap way. And we use the appropriate hardware here. Some examples about inference services, for example, model APIs from OpenAI and Google. That's probably the best example of an inference service. Um, if then we want to build our own model, we want to use an open source model and put it in production and not use one of these closed source models, we will need to build, optimize, and maintain our own inference service. So we will need to have some server uh, that has the models that runs on a specific hardware. It's still in the cloud. We don't need to set up like our own data center, of course. Uh, but we will need to take care about this interaction ourselves. Instead, if we use these model APIs, that's basically leveraging. We're gonna leverage OpenAI and Google's service for that. And and if we want to improve their latency, there's nothing much we can do. In this case, we have lots of more flexibility and we can do it. Of course, it will take more time. Probably it's going to be expensive to do it in the beginning, and we will need expertise from different fields. That is something that is not impossible. So that's kind of the overview about inference optimization. Now we're going to discuss about some common computational bottlenecks, which are the things that make optimization hard. So optimization, as it says in here, it's about identifying these bottlenecks, stuff that just takes more time to run or it's expensive to run, and try to address them, right? So there's a bottleneck, and inference optimization is about, okay, how do we fix this? Yeah, indeed, an inference service should be designed to address these computational bottlenecks. Uh, so there's two main type of bottlenecks. There's compute, one that is called compute bound, and one that is called memory bandwidth bound. So the compute bound refers to the task whose time to complete is determined by the needed by the computation needed for the task. So one of the most common examples is password decryption. So let's say we want to, I don't know, for some reason we want to decrypt a password. And if we just try brute force, we are limited, we're bounded by the by the complexity of the task, right? And in memory bandwidth bound, these tasks are constrained by the data transfer rate within the system, just such as the speed of movement between memory and processor. So in this case, a common example is, let's say we want to make a task. We have a model that needs to move data from CPU to GPUs. So this data exchange takes time, right? And if it is not optimized, we will always be constrained by the data transfer, the movement of data being copied from a CPU to then a GPU, and maybe then we need to copy again to a CPU and send the information to the end user. All of this copying takes time, and we're just bounded by the memory capacities of the hardware. So those are two types. So one, it's we're bounded about the complexity of the problem, the intrinsic complexity, and the second one is more about the specifics of the system and the speed of the memory and its processors and interaction within them. Right? Just a second. So, for example, the author says that the inference for image generation, like a stable diffusion, is typically compute bound, and inference for auto-regression language models is typically memory bandwidth bound. Just two common examples and their bottlenecks. Um, The author also discusses about online versus batch inference APIs. This is something that is also very common on regular software tasks, right? It's not it doesn't apply just to model and inference optimization. There's many tasks that we can perform online or in batch ways. So what are they? Online, they basically optimize for latency. They're very fast at producing a request. So there's a request, and they are processed as soon as they arrive. So let's imagine the best cases, like most of the software that are designed for how is it called? Like for normal users, as like if you go and make a request on Uber and you ask and you open the app and make ask for a ride, or if you go to Google Maps and ask for the direction of to arrive to some point, or you go to ChatGPT and ask a question about what's the capital of France. Usually, you will get a result in the matter of seconds. So that's an online API. They optimize for latency because they know that uh, their end user care about speed, and they want this problem to be solved as fast as possible. So our request is processed as soon as we send it, basically, as soon as they get it. And then there's this other model to process requests, which are batch APIs, and they optimize for cost. So this is the online APIs are usually expensive, and batch APIs are usually cheaper. And in this case, let's say that the application doesn't have any strict latency requirements, so you can send the results. So you can send the request in batches, basically collections of requests for more efficient processing. And this usually happens. What could be in a scenario? Let's say there's a service that makes forecasts for, I don't know, for a business issue, business problem. There's this company that has this model that makes forecasts, and many other companies or many other services send their data and expect to have a result, but maybe they don't need the result right now. Maybe it's a forecast that the service needs to provide every day. So they basically collect all the requests during the day, and at a specific time, maybe at the end of the day, they produce the forecast for the next day and send it to the users. So they don't need to provide the forecast in an online fashion, but they just can collect them, and when they know that they have enough, they process them to just optimize for cost, and then they send the response back to the users, and that's batch processing basically. Some common metrics for inference optimization. This is also general, not only related to model inference, but stuff that engineers talk, inference engineers care. We already discussed latency, or well, we haven't defined it formally, but we already started saying it. But it basically measures the time from when a user send a query until they receive a complete response. So we ask something to ChatGPT, we click enter, uh, OpenAI gets well, we send the query, then OpenAI uh, process it in an online fashion, and they generate a response. And until the response is actually complete, that time that the task is the latency, basically. Of course, the latency is gonna change depending on the question that we ask and the complexity. So people usually talk about the the median latency, the average latency, the or in terms of percentiles, as it says here. But it's helpful to look at latency in terms of percentiles. So what's latency at the percentile 75 or 90, etc. Um, this one is related to models in actually, and it's called time to first token, and it measures how quickly the first token is generated after a user sends a query. So here, instead of waiting till the response is complete, we're measuring, okay, the user sends a query, sends a question, and the model and the service, how long does it take for the service to return the first token? Uh, so, so we can assume that the time to first token is always lower than the general latency, of course. There's also time per output token, and this one measures how quickly each output token is generated after the first token. So we generated the first token. How long does it take us to generate the next ones? Basically. Then time between tokens and inter-token latency measures the time between output tokens, very similar to the previous one. Measures the time between output tokens. Okay, it's more general than the previous one. The previous one focuses in the difference between the first token and the next ones. And this one is basically between token and token. So let's say between the time between second and third token, second and fourth token, or third and fourth token, etc. It's like the inter-token latency. And we can actually mathematically define latency as the sum of time to first token plus time per output token, and then multiply this by the number of output tokens. And that actually makes sense. Yeah, right. Because yeah, this is the time it took us to produce the first token, and this is the time that takes us to produce the second, third, fourth token measured related from the first one. So yep, and we just multiply. Okay, we take if we take like the average of how long it takes us, and we multiply that by the output tokens, then we have a good view on what the general latency is. Um, Another more metrics. There's one called through throughput. I don't know if I'm pronouncing it correctly. Throughput. Okay. It measures the number of output tokens per second, um, and inference service that measures the number of output tokens per second. Okay, how many tokens do we produce per second? An inference service can generate across all users and requests. So yeah, it is measured in terms of tokens per second, um, or completed requests during a specific time, like requests per second. Instead of looking at the granular view of tokens per second, we just care about requests per second, but also fine because let's say that this one would measure across all users. So if it is across all users, we might be more interested about requests per second. This is directly linked to compute cost, and basically a higher throughput typically means lower cost. Okay, if we focus, there's this trade-off that the author discusses that if we focus on an inference service based only on its throughput and cost, this can lead to a bad user experience because an intrinsic trade-off between this metric and the two previous one that we discussed, time to first token and time per output token. There's a similar metric that is called goodput and measures the number of requests per second that satisfies the software level objective. Uh, this one is a bit more abstract because then we need to define what the software level objective is. But basically, it's the same metric, but we only measure on those one that satisfies the criteria that we defined previously, basically. But yeah, it's requests per second. At the end of the day, it's measuring the same in the same metric. Yeah. Then there's utilization, and this one is directly linked to hardware and measures how efficiently a resource is being used. So let's say we have CPUs or we have GPUs. Utilization is basically how efficiently are we using them. It can be measured in terms of MFU, that is called model flops per second utilization, um, or model bandwidth utilization. So yeah, they're more like hardware metrics that we can care like, okay, we're not using the full capacity of the GPU. Why? Is there like a restriction on the software and we cannot like send all the tasks directly to like allocate them and take the most advantage of the GPU? That maybe that there's a bottleneck there. If we fix it, we can utilize more our own hardware and return responses faster, for example. Speaking about hardware, there's this thing called AI accelerators, and basically, we know that fast. So if we want to have fast and cheap software, to have fast and cheap software, we depend on the hardware that it runs on. If we have a very cheap machine running our software, it doesn't matter that much how optimized our code is. If the hardware is very uh, is small, it has not many memory, not much memory. It's gonna be we're gonna be limited by it, right? So the development of AI models and hardware has been always linked together. So if we go back to 2012 when deep learning became a hit again, what's one of the big reasons why it became a hit back then was that we made lots of hardware development at the time. Before, like deep learning has been a thing for many decades, but we just didn't have the specific hardware. Like we didn't have GPUs, so using this type of models, this type of architectures was just something that is not feasible uh, to solve any business problem, basically. And yeah, people were not that interested in it because it was okay. Yeah, it gives nice results, but at what expense, right? It takes forever to train this type of models. We don't even know how we're gonna use them. It's probably just easier to continue uh, researching about linear regression, ensemble model, boosting models, etc. That we knew how to run them on CPUs. So what's an accelerator? It's basically a chip. It's something, a piece of hardware that is designed specifically to accelerate a specific type of computational workload. So we can think the most common AI accelerator are GPUs. We can also name others. Right now, only we call TPUs, tensor processing units. Um, but yeah, their goal is to just make computation faster. This is something that is still like emerging, and there's now companies designing a specialized chip only for inference. So we basically kind of like we're more mature in the specialized chips for training. Uh, a lot of the advanced like research has been focused on that part and makes sense, right? Because the first part of the model building life cycle, building the model and training it. So we have specialized chips for training these type of models. But now there's a lot of research happening in designing chips for just inference. So maybe inference we don't need much of the stuff that we need for training the model, but and we care more about different things. Um, So GPU memory needs to have higher bandwidth and lower latency than CPU memory. This means that GPU memory requires more advanced memory technologies. This is one of the factors that makes GPU memory more expensive than CPU memory. Because, yes, oh, sorry, where am I? Here. So if your workloads are restricted by compute bound, uh, you might want to look at chips that optimize for flops per second. If you don't know what flops per second is, it's floating operation. How's it? Floating operations per second. Is it? I feel like I'm missing a word. Let me just quickly check. Yeah, floating point operations per second. It's just how many floating point operations we make per second. So yeah, if we are bounded by compute, we might want to look for chips that have a fast processing. If we are bounded by memory, then it might be a good idea to just spend a bit more money and buy chips with higher bandwidth and memory, basically. So yeah, those are like the two tips on getting hardware. Then speaking more about inference optimization per se, or like related to models and AI specifically, we can divide it by model optimization, hardware optimization, and the service optimization. So let's talk about model utilization, optimization. So the idea here is to make the model more efficient. How can we do that? We can take care about model compression, make the model smaller, and so making it faster. We can take a look at the autoregressive decoding bottleneck. We'll see that we know that LLMs are autoregressive architectures, and there's a bottleneck in there. So maybe there's something that we can do to kind of release a little bit, relieve a little bit that bottleneck and make the model faster. And then also in the attention mechanism, maybe there's some things that we can do at inference to optimize that model. So speaking about model compression, indeed, it is the task about like we care here about making the model making the model smaller. So with the hopes to make it faster. There are two common techniques here. One is called quantization, and this is about reducing the precision of the model to reduce its memory footprint and increase its throughput. So basically, here we can accept, okay, I want a less accurate model, but uh, and this trade-off we pay it by having a model that is basically faster to run because it requires a little bit less of memory. That's there's quantization techniques, uh, and that's their goal, right? And then there is distillation that we discussed last week, and it's about training a small model to mimic the behavior of the large model. So basically, that's why it's called distilling. Right? We have a large model, and we want to train a smaller one that kind of behaves and tries to mimic the larger one. And this smaller one is gonna be cheaper to run and faster. Yeah, these are two of the modern techniques for model compression that basically makes our model more efficient. And ideally, it doesn't affect performance that much. Then about overcoming the regressive decoding bottleneck. Uh, Here, the idea is like the hypothesis is that improving the autoregressive generation process by a small percentage can can translate into a better user experience, basically. The author says that perhaps one day there will be architectures that don't have this bottleneck. Right now, the transformer architecture has it. So that's why we talk about it, right? There's this technique that is called speculative decoding. Um, It uses a faster but less powerful model to generate a sequence of tokens, which are then verified by a target model. So, so we have two models. One generates the sequence of tokens. So this model is faster. This model is cheaper, probably less accurate, but it's just faster at generation. And then there's a target model, which is better, uh, more expensive to run. And this target model, what it does is verifying the output of the chip model. So yeah, the faster model is called the draft or proposal model because it produces the draft output. I think I have an image. Yes. So how's this? So yes, this is so there's let's say we have this text and there's these predictions that a faster model, a draft model makes. So I saw a dog right, and then the draft model outputs in the bus, and then there is a target model that is more accurate, more precise, and verifies each of the outputs of the draft model. So I dot write in and checks, okay, that passes. That checks, and then car, okay, no, that didn't. That was a bot token. So maybe there's a process in there to generate a new token, and the target model verifies it. So the time it takes for target model. So the whole idea here, we have two models, right? And it might seem very complex, but this idea makes sense when the time it takes for the target model to verify a sequence of tokens, is less than the time it takes to generate it. So let's say we have like this big LLM, this intelligent one, but it's not super good at generating tokens. There's a bottleneck in there. So, and we have this other draft model that is faster at that. So we basically use it as a model that just produces things, and we use the intelligent one as a model that verifies things. So if that's the case, uh, then this is a good idea to maybe run this type of process. Carlos, I see you have a question.
Yeah, I just wanted to point something because I was a bit confused about this yesterday when I found it.
Mm-hmm.
And I posted a video that is in the Discord just in case someone wants to take a look at it. And what I found is that apparently I didn't understand why was the big model, going to actually take less time if it has to receive a sequence of tokens and decide what's the possibility of each of the tokens. Because at first I was thinking, okay, that's going to take actually the same time. Why is it going to take less time than actually generating? Because it's the same task. But apparently one of the tasks that takes a lot of time when you're generating tokens is the sampling. And
Mm-hmm.
apparently the thing that you do when you apply this technique is that the second model does not sample. It just generates and compares. So it's a different process. So the one that is going to be sampling, so doing the entire generation of the token, so gets the logits and chooses a token and then does all of the that is going to be only the tiny model. So I guess that's what actually makes it faster.
Yeah. When I also read it, this was okay. This seems like a lot. There's happening a lot of things. I don't. It's hard to imagine a process where all this, even like data transfer and interaction between two models, it's gonna make it more efficient. But indeed, so thanks for the explanation. Yeah, I wasn't. I saw your question yesterday, but I didn't saw the video. Interesting that yeah the process the bottleneck here is sampling, and basically cheaper models or smaller models are faster at sampling. Great. But yeah, that's the general idea. There's another approach which is called inference with reference, and the this one is relatively easy to understand with an example. So for example, if we are doing question and answering, and we and we send a document to the model. Let's say what I don't know. It's a summarization task, or we send a document to a model just to the model has the full context, and we can want to ask questions to this document. The question and answering model might repeat a chunk, like literally, its response can be a chunk from the attached document. And this is what we call reference. So this attached document is a reference. So the model doesn't need to waste or spend that much time in generation, because it detected it went to the document, it parsed it, and it detected, okay, this chunk actually answers the question the user is making. So the whole autoregressive bottleneck, autoregressive decoding bottleneck doesn't necessarily happen for all the tokens that are because it literally just sent a big chunk of text that found it in the document. Similar that if you ask the model to fix bugs in a piece of code, the model might reuse the majority of the original code and just make tiny changes. So it doesn't need to generate all the code that you are already wrote. It just needs to detect where the implementation, where the tiny changes needs to be done, and they generate that specific part. So the core idea is to copy tokens from the input to speed up the model generation. That's basically it. And the author says that if you think about it, it's actually kind of similar to speculative decoding, the approach that we just discussed. But instead of using a model to generate draft tokens, so we had this small model generating these draft tokens and a model verifying them. Instead of having a model to generate those draft tokens, we select draft tokens from the input. So having a reference kind of solves the issue of having two models. So if we think of this if we think about these draft tokens as a reference, it is kind of the same thing, right? We have a reference, and then the model selects those tokens from the input. That's the general idea about inference with reference. In this one, yeah, we assume that we always have a reference, right? So it cannot be done for every task. It's just task that you have an input reference. Then, so we discussed about model compression, overcoming autoregressive decoding bottleneck, and now let's take a look at attention mechanism optimization. So in chapter 2, and also in the previous book that we read, not wrote, that we read, we saw that generating the next token requires some vectors, requires the key and value vectors of all the previous tokens. So for example, if we want to generate the X token on this specific time, we required the key and value vectors of tokens and of the first token, second token, up to the previous token up to the X t minus 1 token. And generating the next token, xt plus 1, requires a key and value vectors of first, second, x t minus 1, and the previous one, xt, right? So the whole idea here is that in inference, right? We talk about inference. The whole idea here is that instead of computing the key and value vectors for tokens for all the previous tokens, again, we reuse these vectors from the previous step. So basically, it's about having a cache, having a place where we can store key and value vectors, and we just reuse them for all the operations that we need them. As I said, this cache is only makes sense during inference and not training, because during training, all tokens in a sequence are known in advance, and the next token generation can be computed all at once instead of sequentially, as during inference. So there's no need for the key value cache in training. So there's an image, I think. Oh, I didn't put an image. Did I have an image? No. But yeah, that's the general idea, that we basically store in a place all the previous key and value vectors and just reuse them instead of having to compute them every time by inference, which kind of makes a bit of sense. So we don't double compute things. And that's about model optimization. Any questions?
I have one question about catching KV values that I never understood, which is in order for a catched pair of values to be valid, you would need to have found the tokens in the exact same place, right? Because normally you have this position embedding before. So there is some information about where each of the words was found. So if two queries of the user have the same tokens, but in different positions, just because one of them added hello at the beginning, then you cannot take advantage of the catch, right?
Yeah, you cannot use them directly. Yeah, that is true. That's a good question.
Maybe there are strategies for that. I just never.
Probably there are. And probably is you don't store them. So probably you store them without taking into account the positional embeddings, and you take that into account.
After.
Then when you apply those key and value vectors, because indeed then it's gonna be different. You just store. Yeah, probably positional embedding is something that you don't cache. It's not aggregated in that cache. But yeah, I also something that's outside my knowledge. A good question indeed. Then the chapter ends with an explanation about inference service optimization. So what are we gonna discuss in here? Batching. So yeah, this is about techniques that focuses on how to optimize our resources. So here we talk about batching. It's one of the easiest way to reduce the cost of computing things. So instead of processing each request separately, batching aggregates requests, puts all of the of similar requests in the same batch, and we just process them together. If processing each request separately is okay, the author makes an fun analogy, that processing each request separately is like everybody drives their own car, and batching is like everybody takes a bus. So a single bus has, I don't know, 50 people inside, instead of having to have 50 cars in a street. So static, there's two main types of batching: static, and in this one, the service groups a fixed of numbers. The service groups a fixed number of inputs together in a batch. So it's like the author makes an analogy there that is like, okay, there's a schedule, and the bus doesn't go until the bus is filled is filled with a specific amount of people. So let's say the bus only moves when there's 30 people inside. It can allocate 50 people, but it won't go to the next stop if we only have 10. It just needs to have 30. So we collect the 30, okay, then it moves. It goes to the next stop. And dynamic batching, it sets a maximum time window for each batch. And this is how most of the buses that I know works. There's a schedule, and the bus is in the stop. Few people get in, can be 50, can be 2, but the bus now has to comply with a specific schedule and get to the next stop on a specific time, so the bus just goes. Here's an image that kind of visualize and represents this type of batching dynamics. So here we have requests that were made every time, and in static batching, let's say here we care about having at least 4 requests per batch. So here when if we collected three requests that were like very next to each other, there was a space where something didn't happen. But then we collected the fourth. Okay, we process this batch. Similar with this, similar with this. And in dynamic batching, uh, in this one, we don't care about how many requests are in a single batch, but how many requests we process together per time in a specific window of time. And here, we don't care that we don't have four. We just care about the size of this specific window. So we process three. And here we process four, three. And here we process two. So that's the difference between static and dynamic batching. And this, of course, can optimize our service, can optimize our not the model, but I'll optimize the service that we provide, the cost. But of course, this only applies if it makes sense for the business and how we solve the user problem, right? Because maybe, like for example, maybe ChatGPT has some dynamic batching happening because it receives many requests per second, right? It's the whole world using it, and we kind of see it as an online fashion. Like we send a request and we receive almost immediately an output. But inside of there, that might be like some batching strategies happening that are just very fast. But yeah, this window doesn't need to be like in terms of days. That's what I wanted to say. Like it can be as fast as milliseconds or seconds. And just because the service is used by many users, these batches are always filled. Another strategy to optimize the inference service is decoupling, prefill, and decode. So we know that LLMs inference consists of two steps. The prefilling it's computed bounded, is compute bounded, and decoding is memory bound. We're bounded by the memory bounded. So the idea here is to use different hardware basically for each of these tasks. So yes, one common optimization technique for inference service is to basically separate the prefilling task and the decoding task because one, we need basically to make many operations, many flops per second in this one. And this, so we need hardware that is able to just do many flops per second. That can be like cheaper to get than hardware that we just need lots of memory. So we basically say, okay, for all the prefilling tasks, let's allocate those requests to this specific type of compute. And for all the decoding tasks, let's allocate those tasks to a very good, nice GPU that has lots of memory bandwidth. And that's one of the inference service optimizations that you could do. And another strategy is prompt caching. Yeah, useful when we have long documents. An example is, let me see, because I actually don't remember. I have to read. If many of your user queries are related to the same long document, such as a book or a code base, okay, yes, this long document can be cached for reuse across queries. Now that I read it, it sounds very similar. I mean, it's different, but sounds. I kind of recall the idea of RAG here, where yes, we have a reference document, we have a book, a code base, or something that we are gonna use many times, so we can just cache that somewhere instead of having to give this context to the model and the model to process this context every time the user makes a request. So basically, we can reuse this information across different queries. So this can reduce, it's a relatively easy way to reduce latency and cost because we don't have to go and basically give this context to the LLM every time we make a request. Then, of course, parallelism, something that has been, I don't know, in the interest of engineers for a long time. And this is actually like the backbone of high performance computing. And this is something that GPUs do very well. But there might be things that we can do even better and parallelize more. So often we have a model that is so big that it doesn't fit on a single machine. So we need to parallelize those tasks. And that means we need to split it some way and basically split the tasks in many different computers, in many different pieces of hardware to run things. And then we kind of merge together all the answers or the outputs in an intelligent way. And ideally, that splitting and processing in independent units is faster than just running things sequentially. Or it's not only faster, but it's also possible because sometimes you can actually not fit everything in a single machine, right? So there's two common ways to split a model. One is called tensor parallelism, and the other one is pipeline parallelism. So the tensor one, an example is that when multiplying two matrices, you could split one of the matrices column-wise. We have a visual here about tensor parallelism. So let's say we have this matrix, and we want to multiply it by this matrix, and we get this result. This is the non-distributed way, right? The regular way, the one that you would even do manually. If we distribute this in two devices, let's say we have this main matrix, still the same, and we split this one by two. So we send this column vector to one of the devices, plus a copy of the original matrix here. We multiply, get this result, and just store that somewhere while the other task finishes. And in parallel, there's also this process happening. We have this matrix, we have the second column of the second matrix, we multiply, get the result. When both tasks are finished, there's a reducing process. There's a putting everything together process where we just have the final outcome. So when is this useful? When we cannot fit these two matrices in a single computer, right? That's useful. So let's say this computer is small and we cannot fit these things. So we cannot get this result. So we get two, could be even like two small computers that are able to fit half of this matrix plus the original matrix. So we just use two small computers, two small workers that are able to do the task separately, and then we just merge everything together. And it's also useful when just you have, here we have two devices, right? But we could have n devices. If this matrix has like more columns, we could have three devices running the same process in parallel and then just gathering all the results. So that's one way of splitting the model, tensor parallelism. And the other one is pipeline parallelism, and it involves dividing the model's computation into distinct stages and assigning each stage to a different device. A visual for that is that, just a second to open the door. It was my dog that wanted to come to the office. So in this view, instead of like splitting the data, here we split the stuff in different processes. So here, these MB1, they are mini batches of data. So let's say we have like this kind of model architecture where we have 4 layers. There's this data coming in, and this first device, this first computer, takes care about all these layer 1 processes. And then the second one takes care about all the layer 2. So basically, in this specific pipeline, in this specific example, we have as many devices, as many layers we have, and we parallelize the operations in that way. So we don't look at it in this granular way that we split all the multiplications, but here we're splitting the pipeline, basically. Of course, inside, we could even have this type of tensor parallelism. So all the computations that happen inside here might be also be performed in this fashion. And there probably are if we are making these operations in a GPU. So you can think about this as a GPU computations that are happening inside here. And this pipeline parallelism, it's been orchestrated by other software on top, right? So yeah, that's about inference service optimization. And I think that's the end. So in summary, we discussed about the basics of optimization, where we discussed about the overview, computational bottlenecks, online and batch inference APIs, some common performance metrics for measuring how optimized our inference is, AI accelerators, and then some strategies to do model and inference service optimization. Any questions, comments, or concerns?
No, thanks for the work, Santiago. I just asked on the background OpenAI about the question about the KV caching values, and
Yes.
apparently there is a quite easy to understand answer, which is it actually does not make sense to share the cached values between different prompts of the user. But when you have one prompt, let's say that the prompt has 4 tokens, the prompt of the user, then you are going to feed that to the model. It's going to have to do those 4 multiplications. It's going to generate another token. And from that point on, if you look at that, the next token, you already multiplied the 5 values, and even their positions are not going to change for the next tokens. So basically, it's about catching when you do this kind of regressive generation. So makes sense, actually.
Yeah, makes sense. Nice. Nice. Yeah, interesting. So you asked ChatGPT for the explanation, or nice.
Yeah. Okay.
Cool. All right. Yeah. Anything else? Any other question? Nope. So this was chapter 9. We're just missing one chapter. So I don't know if from the few that we are here, if there's anybody would like to take the lead on the last chapter, and we finish the book next week.
Okay, I'll do it.
You can do it. Nice. Thanks, Carlos. Happy to see you back in the meetings as well. Yeah, so if everything goes well, next week we'll finish the chapter and we'll finish the book. Well, next week we'll finish the book. What do I wanted to say? Yeah, some people ask if we're reading something next in the following weeks. We could. I actually have no idea what we would like to read. So maybe we can open like forum and define. My only concern is that I'll be traveling for work. Like, actually, I travel next week, but in the night, and the schools are in my morning, so everything's fine. But yeah, we can just accommodate things. But yeah, let's discuss that async and decide on a book first. It doesn't need to we don't need to start reading right away.
Also, if we decide to read something, we're going to have June and July and some difficult months for coordinating a group. So we can talk about that and see if we keep maybe we change the schedule or something like that. Yeah, let's talk about that.
Indeed. Yeah, we can have a couple of some weeks that we just rest. People rest while we decide, and then yeah, we just kick off a new book in another month. But yeah, good. Thanks, Carlos, for taking the lead on the last chapter. Very excited about it, and yeah, see you there.
Yeah, thank you. Nice job.
Bye.